Section 3.2. So in the last section, we covered inductive reasoning, and we also touched on deductive reasoning a little bit. So in this section, section 3.2, we're going to get a little bit deeper with deductive reasoning, as well as explore this concept of validity, of statements being valid or invalid. So just reminding ourselves a little bit. So deductive reasoning is whenever we are going to make conclusions based on facts. Okay, so the other day we talked about inductive reasoning and deductive reasoning. So inductive reasoning was when we make conclusions based on observations. Deductive reasoning is when we're going to make a conclusion based on facts. So deductive reasoning is going to be something that mathematicians use all the time. So any kind of idea that we kind of accept as a truth in math, for example, anytime I take two even numbers and add them together, I'm always going to get an even number. The way that we know that these things are valid is because we have mathematicians who they've gone through and they've used definitions, properties, postulates, and theorems to prove that those kind of basic statements that we already accept as truth, they've already gone through and done the hard work for us. So let's dive a little bit deeper into this stuff now. So now we're going to talk about this idea of validity. Okay, so the definition of validity is being deduced or inferred based on facts or evidence. Okay, so one important note I want to bring up is that validity and truth are not necessarily going to be the same thing. Something can be a true statement, but not necessarily be a valid statement. Okay, and as you see right here, a statement is going to be valid if it follows the rule, and we'll kind of explore what that rule means. Okay, so let's look at a few examples. So right here, we're asked, determine whether the stated conclusion is valid based on the given information. And if not, we need to write invalid and then explain our reasoning either way. Okay, so here's our rule. Okay, so we talked about earlier how a statement is only valid if it follows the rule. So here's our rule that we got to follow. If two angles are vertical angles, then they are congruent. Okay, so that's our rule. So that is going to be true 100% of the time. If two angles are vertical angles, then they're going to be congruent. That is 100% true 100% of the time. So using that rule, we're given this scenario. We're given a scenario of having two angles, M and N, and M and N are congruent to one another. Okay, so that's what we're given. And so our conclusion then is that angles M and N are vertical angles. Okay, so at first you're probably thinking, well, if we look at our rule, if two angles are vertical, then they are congruent. So if we're given two congruent angles, they must be vertical. That just kind of makes sense. But when we're determining if a statement can be valid or invalid, we have to think about this. Is this situation, is it true 100% of the time like our rule is? So basically what I'm saying is that is any time that I've got two angles that are congruent, is every single time that they have to be vertical angles. That is, vertical angles mean two angles that look similar to this picture. So this would be a case of two angles being vertical right here. So is it that every time that I have two congruent angles that they can look like this? Well, we can have congruent angles that come in all shapes and sizes, come in all different forms, okay? We could have two right angles that we draw right here. And as we can see, we could call these angles M and N. And here, two congruent angles, so we're following our given, but they're not vertical angles. So again, right here, I've got two angles, and these two angles, they're also congruent to one another, but they're not vertical at all. So because anytime that I have two congruent angles, they're not always vertical, this is an invalid statement. So when we're looking for a statement to be valid or not, it's got to be the case of where 100% of the time, that's the only conclusion that we can have. Okay, so let's look at the second example. So the second example, still following our same rule. If two angles are vertical angles, then they are congruent. So our second example, we are given that angle X and angle Y are vertical angles. And so our conclusion then is that angle X must be congruent to angle Y. So in this one, the scenario is kind of flipped. So up here, we were told that we're given two congruent angles. Here, we're told that we're given two vertical angles. So we learned from our rule that any two angles are vertical, then they're also going to be congruent. So we're given two vertical angles and our conclusion is that they're congruent. And that is going to be a valid statement because there's no scenario where I could have two vertical angles and they not be congruent. So because of that, this is going to be a valid conclusion. Okay, let's move on to some different examples. Okay, so next up, again, determine whether the stated conclusion is valid based on the given information, and if not, we need to write invalid and explain our reasoning either way. So once again, they give us a rule here to follow. If two numbers are odd, then their sum is even. Okay, so this is the rule. Anytime you take two odd numbers and you add them together, their sum will be even. 100% true 100% of the time. So having this rule, we're given the scenario of having the numbers 3 and 11. And our conclusion then is that their sum must be even. So if we look back at our rule says that if two numbers are odd, their sum must be even. And we are given two odd numbers, 3 and 11. So even if I don't necessarily know what their sum is, which we can quickly figure out that it's 14, even if I don't know what their sum is, as long as I know that 3 and 11 are two odd numbers, then I can assume that their sum must be even. So this is a valid statement. Okay, in this situation, I'm given the numbers 2 and 7. Again, same rule. If two numbers are odd, their sum is even. So I'm given the numbers 2 and 7, and my conclusion is that their sum must be even. Well, this is going to be an invalid statement because the rule was if I'm given two odd numbers, their sum is even. But I'm not given two odd numbers here. I'm given an even number, 2, and an odd number, 7. So I can quickly figure out that their sum is definitely not an even number. But because I'm not given two odd numbers to begin with, this statement was invalid from the beginning. Okay, let's look at a few more examples. All right, so we're just kind of seeing all the different ways that we could determine if statements could be valid or not. Okay, so here we are to determine if a conclusion, determine a conclusion that follows from the statements 1 and 2, and if a valid conclusion does not follow, we would just write no valid conclusion. Okay, so rules a little bit different this time. So they didn't give us a rule. Well, they did give us a rule, excuse me. That's going to be our first statement. Okay, so let's look at these. Statement 1, if n is a natural number, then n is an integer. So we are given, so this is basically kind of our rule. Anytime n is a natural number, then n is going to be an integer. And so then our second statement, n is a natural number. Well, based off our first statement, anytime n is a natural number, n is going to be an integer. So if we're given that n is a natural number, a valid conclusion that we can draw will be that n has got to be an integer. Okay, let's look at the second one. If it is Saturday, then I do not have to go to school. Okay, so if it is Saturday, then I do not have to go to school. My second statement, I did not go to school today. Well, here's the thing. We're looking for a valid conclusion, and that meaning that there's only one possibility that this could go down based off our current scenario. So anytime that it's Saturday, I don't have to go to school, okay? So if our second statement here was that it is Saturday, then a valid conclusion could be I do not have to go to school. But they give our second statement as I did not go to school today. So we can't necessarily just put it is Saturday because there's a lot of reasons why you maybe didn't go to school today. You could be sick. Your car may have broken down. You know, it could be snowing. There's a ton of reasons why you decided not to go to school today, not necessarily that it's just Saturday. So because there's a ton of possibilities, based off these two statements alone, there's no valid conclusion that I can draw. Okay, let's look at this last one. If x equals 4, then y equals 7. And then if y equals 7, then z equals 12. Okay, so this is kind of a one depends on the other type issue. Okay, so for this one, if I was to draw a valid conclusion, what I can basically do is I can try to cut out the middleman. So I know that if x equals 4, then y equals 7. And I know that if y equals 7, then z equals 12. So if I want to just cut out the middleman, I'm going to cut out the thing that is the same in both of them, y being equal to 7. So then I can just connect these two together and write my own valid conclusion that if x equals 4, then z is going to equal 12.